Chapter 4 Reactions in Aqueous Solution. Section 4.1 General Properties of Aqueous Solutions. A solution is a homogeneous mixture of two or more substances. The substance present in the greatest quantity is usually called a solvent, and the other substances are called solutes, and they are said to be dissolved in the solvent. When a small amount of sodium chloride, NaCl, is dissolved in a large quantity of water, for example, water is the solvent and sodium chloride is the solute. Electrolytic properties. At a young age, we learn not to bring electrical devices into the bathtub and not to electrocute ourselves. That's a useful lesson because most of the water you encounter in daily life is electrically conducting. Pure water, however, is a very poor conductor of electricity. The conductivity of the bath water originates from the substances dissolved in the water and not from the water itself. Not all substances that dissolve in water make the resulting solution conducting. Imagine preparing two aqueous solutions, one by dissolving a teaspoon of table salt in a cup of water and the other by dissolving a teaspoon of table sugar in a cup of water. Both solutions are clear and colorless, but they possess very different electrical conductivities. The salt solution is a good conductor of electricity, whereas the sugar solution is not. In order for the bulb of the device to light up, there must be a current, that is, a flow of electrically charged particles between two electrodes immersed into the solution. The conductivity of pure water was not sufficient to complete the electrical circuit and light the bulb. The situation changes when ions are present in solution because the ions carry electrical charge from one electrode to the other, completing the circuit. Thus, the conductivity of sodium chloride solutions indicates the presence of ions. The lack of conductivity of sucrose solutions indicates the absence of ions. When sodium chloride dissolves in water, the solution contains sodium ions and chloride ions, each surrounded by water molecules. When sucrose dissolves in water, the solution contains only neutral sucrose molecules surrounded by water molecules. Figure 4.2. Electrical conductivities of water and two aqueous solutions. Pure water does not conduct electricity and doesn't light the light when connected to a battery. A sucrose solution, sugar, is a non-electrolyte and does not conduct electricity. Sodium chloride solution, NaCl, is an electrolyte and does conduct electricity. A substance such as a salt, whose aqueous solution contains ions, is called an electrolyte. A substance such as sugar that does not form ions in solution is called a non-electrolyte. The different classifications of NaCl and C12H22O11 arise largely because sodium chloride is ionic, whereas sucrose is molecular. Ionic compounds in water. Recall from figure 2.21 that solid sodium chloride consists of an orderly arrangement of sodium and chloride ions. When sodium chloride dissolves in water, each ion separates from the solid structure and disperses through the solution. The ionic solid dissociates into its component ion as it dissolves. Figure 4.3, Dissolution in water. When an ionic component such as sodium chloride, NaCl, dissolves in water, water molecules separate and surround and uniformly disperse the ions into the liquid. Molecular substances that dissolve in water, such as methanol, usually do so without forming ions. We can think of this by simply mixing two molecular species. Both A and B, the water molecules, have been moved apart so that the solute particles can be seen clearly. Water is a very effective solvent for ionic compounds. Although water is an electrically neutral molecule, the oxygen atom is rich in electrons and has a partial negative charge, denoted by a delta negative. Each hydrogen atom has a partial positive charge, denoted by a delta positive. Cations are attracted by the negative end of the water, and anions are attracted by the positive end. As an ionic compound dissolves, the ions become surrounded by water molecules, as shown in Figure 4.3a. The ions are said to be solvated. In chemical equations, we note solvating ions by writing them as sodium ion, and chloride ion, where aqueous is an abbreviation for aqueous, AQ. Solvation helps stabilize the ions in solution and prevents cations and anions from recombining. Furthermore, because the ions and their shells of surrounding water molecules are free to move about, the ions become dispersed uniformly throughout the solution. We can usually predict the nature of ions in a solution of ionic compound from the chemical name of the substance. Sodium sulfate, for example, dissociates into sodium ions and sulfate ions. You must remember that the formulas and charges of common ions, tables 2.4 and 5, to understand the forms into which ionic compounds exist in aqueous solution. Molecular compounds in water. When a molecular compound dissolves in water, the solution usually consists of intact molecules dispersed throughout the solution. Consequently, most molecular compounds are non-electrolytes. As we have seen, table sugar, sucrose, is a non-electrolyte. As another example, a solution of methanol, methyl alcohol, in water consists entirely of methyl alcohol molecules dispersed in the water. A few molecular substances have aqueous solutions that contain ions. Acids are the most important of these solutions. For example, when hydrochloric acid dissolves in water to form hydrochloric acid, when hydrogen chloride dissolves in water to form hydrochloric acid, it ionizes. That is, it dissociates into hydrogen proton, aqueous, and chloride ions, aqueous. Strong and weak electrolytes. Electrolytes differ in the extent to which they conduct electricity. Strong electrolytes are those solutes that exist in solution completely or nearly completely as ions. Essentially, all water-soluble ionic compounds such as sodium chloride and a few molecular compounds such as hydrochloric acid are strong electrolytes. Weak electrolytes are those solutes that exist in solution mostly in the form of neutral molecules with only a small fraction in the form of ions. For example, in a solution of acetic acid, most of the solute is present as acetate molecules. Only a small fraction, about 1% of the acetate or acetic acid, is dissociated into hydrogen ion and acetate ion. We must be careful not to confuse the extent to which electrolyte dissolves, its solubility, with whether it's strong or weak. For example, acetic acid is extremely soluble in water, but it is a weak electrolyte. Calcium hydroxide, on the other hand, is not very soluble in water, but the amount that does dissolve dissociates almost completely. Thus, calcium hydroxide is a strong electrolyte. When a weak electrolyte such as acetic acid ionizes in a solution, we write the reaction in the form acetic acid, aqueous, yields, as a double arrow, acetic acid is acetate ion, and hydrogen ion. The half arrows pointing in opposite directions mean that the reaction is significant in both directions. At any given moment, some of the acetic acid molecules are ionizing to form hydrogen and acetate ions, but hydrogen and acetate ions are recombining to form acetic acid. The balance between these opposing processes determine the relative number of ions and neutral molecules. This balance produces a state of chemical equilibrium, in which the relative numbers of each type of ion or molecule in the reaction are constant over time. Chemists use half arrows pointing in opposite directions to represent the ionization of weak electrolytes and a single arrow to represent the ionization of strong electrolytes. Because HCl is a strong electrolyte, we write the equation for the ionization of HCl as HCl, hydrochloric acid, aqueous, yields unidirectional arrow as hydrogen ion, proton, and chloride ion. The absence of a left-pointing arrow indicates that the hydrogen ion and the chloride ions have no tendency to recombine to form hydrochloric acid molecules. In the following sections, we will look at how a compound's composition lets us predict whether it's a strong electrolyte, a weak electrolyte, or a non-electrolyte. For the moment, you need only to remember that water-soluble ionic compounds are strong electrolytes. Ionic compounds can usually be identified by the presence of both metals and nonmetals. Ionic compounds containing the ammonium ion, for example, are exceptions to this rule of thumb.